about my summary.
Awesome. Thank you so much, David. And I'm sorry that I couldn't make it in person, but I'm excited to share about our spring survey result of giant plants and brown companions today. And before I get started, I would like to shout out to all of the KPIC team members who enables the discovery that I'm presenting today. So one of the questions that we are really hoping to answer is if we can differentiate through any of the observables between giant planets and brown dwarfs. And here is a beautiful movie made by Jason Wang et al. Using Keck 2. So this is a beautiful HR79 system for planets, and then we can not only see the beautiful orbits, but also we can try to study their orbital dynamics. And previously, Bowler et al. Has found evidence of different orbital eccentricities between giant planets and brown dwarf companions. That's exciting. And recently, there's a lot of spectroscopic follow-ups within these giant planets and brown dwarf companions as well. And here's the Keck Osiris spectra by Konopaki et al. That shows the HI799C planet that shows a clear CO and water band. And we're also interested about seeing if there's any differences in the spins. And one of the motivations that we want to see the spin is because the theory actually predicts the differences of a terminal rotational velocity between the giant planets and brown dwarf companions as a function of mass. The main mechanism is because of the disk breaking. So that's just because the planets or brown dwarf companions, their magnetic field scales up as a function of mass, and the interactions with the thermal ionization of the disk kind of determines how much disk breaking will happen during earlier stage. And later on, they just undergo spin up. And the spin up relation is actually well known through observations. The first evidence was actually done by using Keck spec by Zapatero Osorio 2006. And later on, Brian et al. Also follow up with a few planetary mass objects and a lot of brown dwarf companions and show similar evidence. And here's to show the a huge rotational period survey by Voss and al. That shows the spin up trend as a function of ages for brown dwarfs and free-floating planetary mass objects. What about the mass? This is actually not so clear. Before this work, actually, we had a paper last year try to look at the trend using a few literature measurements as well as a bunch of KPIC publication. So this is a normalized spin as a fractions of breakout speed and a given age. This is a 5 years. So we can see, although we're hoping to see a trend as a function of mass, this is just a scatter plot. And one of the issue is that there's a lot of different instruments and methodology by combining both the VSI and rotational period surveys. And what's more challenging is because this planet thing has only 3 planets in one HR79 system. So that makes seeing the trend very challenging. They kind of motivates us to push in more planet observations and also more uniform analysis of the sample. So what we use today is KPIC. And what is KPIC? As a reminder, this is a high resolution spectra that uses the fiber injection unit connects to our old friend Keck spec with a resolution out of 35,000. And we can target a lot of recently discovered image planets and brown dwarf companions. And this is just to show if we can put one of 4 fibers on the planet or brown dwarf companion location, and the light will be dispersed into these 2-dimension spectra shown on the right. And Chas also kind of highlight that we are also pushing the H-band with LFC capability. And also, Luke Finley later today will be talking about his Hot Jupiter results using the L-band KP spectroscopy. So there's a lot of image planet and brown dwarf companion discovery over the past few years. And KP has followed up and we have already detected 30 of the companions. And all of these are galleries of all of detections starting from planetary mass from 2 Jupiter masses all the way to 90 Jupiter masses or so. And we have published a majority of these sources of using our KP follow-up data. And most of these have actually discovered by either SCATS-AO or NEC2 by Cal Franzen and Brennan Bollier. So we are able to probe a lot of different chemistry, not just the spins. And today we'll be focused on the spin. And here's one illustration of how we can constrain the spins here. So here is a brown dwarf companion about 40 to 50 Jupiter masses. And then this is a cross-correlation function detection that's in magenta. And you can see this CCF wins is actually broadened compared to the non-broadened autocorrelation function of the template. That basically indicates we have the spins imprinted in the spectra. And we can also do the forward modeling to do a more precise assessment determination of their atmospheric properties. We can determine effective temperature, surface gravity, radial velocity, and most importantly, the V psi I. And this is a moderate rotator, which is 53 kilometers per second in terms of spin. And the first thing that we can check our sample measurements is we can check V psi as a function of ages. So we have the ages mostly from their host stars. A lot of host stars are in the young clusters of the moon group. And we just rediscovered the well-known spin-up trend, which is nice, and also validate our result. And also, 90% of our sample are fully consistent with the literature measurements in terms of V psi I. And to derive our spins, we actually need to do some more work to analyze its true rotational velocity. So the rotational velocity is a function of V psi I, and then we need to disentangle this psi I factor, which is inclination. So we can either assume the random or uniform inclinations, or inclinations align with the orbits. And we also need to normalize as a function of breakout speed. And breakout speed is a function of GM over R square root. The mass, a lot of times we have dynamical masses or model masses. And the radius, we use sub-stellar atmospheric models. We have the masses from above and ages from the host star. And finally, we need to disentangle this age factor, this spin-up trend, and we can assume constant angular momentum and evolve back. In this case, we assume 10 million years. So here is one of the questions we want to make sure our sample is fine. So what is a planet? So first, we can think about these like famous image planets or planetary mass objects in terms of masses. So we define the bona fide planets masses below 10 Jupiter masses. And we can think about also the mass ratio of mass ratio below 0.8%. So the overlapping these bona fide planets are labeled in red. And then these transitional objects that satisfy only one of the two criteria are labeled in magenta. We also incorporate some of the literature sources, which is about 10 objects using mostly Quartus plots, for example. And here is our result. So we try to look at these normalized spins, the fractions of breakout speed as a function of mass and 10 million years. And we see this red, the bona fide planets are showing fast rotation compared to these frontal commands showing in blue as a slower population. And this transitional object kind of scattered in between, that is in the mass space. And if you look at the mass ratio space, this actually makes a more clear cut. So that means both mass and mass ratio are important in separating these two populations, and spins are actually pretty exciting in disentangling their formation pathways. And we can also assess the significance of these differences among these two populations. So we can kind of populate these measurement uncertainties and then make a distribution of the means, for example, among the giant planet population. And then we can measure fit a Gaussian and measure the dispersion compared to the brown dwarf population. And what we found is that when we assume their orbits are aligned, which the components inclinations align with the orbits, they actually show more than 3 sigmas significance between the giant planets and brown dwarf companions. And when we assume random inclination, this significance is lower at 1.6 sigmas. But these are definitely showing distinct populations even by looking at the posteriors of the mean distribution. And here's my takeaway. I hope you are convinced that this is exciting result of the spins between giant planets and brown dwarfs that shows different levels of spins. I'll be happy to take any questions. Thank you.
Hi, buddy. I